Last episode, we opened the right half of CIC, inductive types as constructors and eliminators. The left half, CC omega, we left closed. A promise that the omega subscript was a story for another time. Today we open it. 4 ideas. First, a hierarchy of universes. 2 flavors of quantification. 2 readings of what proof means. And 1 principle deciding whether equality proofs themselves can differ. The cheapest design would be to let every type live in one universe, including that universe itself. Set theory tried this once. Russell's paradox form the set of all sets that don't contain themselves. It leads straight to a contradiction. Type theory has its own version. With type as its own type, Girard in 1972 and Herkens later, in a tighter form, built a closed term of the empty type. The dangerous extra power is closure. If Ea is a type, then the whole type of predicates on Ea is again just another type in the same universe. In Herkens' presentation, this is written like a power set. Power set of A is the space of predicates on A with type. Type. Power set of A stays at the same level as A. That is the loop the diagonal argument needs. Herkens then defines a type U that can talk uniformly about every X, every attempted map from double power set of X back to X, and a new double power set of X. From that self-coding, the proof gets a map from the double power set of U back into U. Then the usual diagonal question can be asked inside the type theory itself. Does the coded predicate contain its own code? Every proposition becomes provable, the theory collapses. So type cannot be its own type. We have to break the loop. The fix is to split type into a tower. Each floor's type is the floor above it, forever. Nat lives at the ground floor. Type 0 lives one up. Type 1 lives one above that. No type ever contains itself, and the paradox loses its grip. An infinite tower of universes stacked on top of COC. That is what the omega subscript names. And that is the system Lean and Rocq build everything else on. One way to keep the tower workable is cumulativity. A type at level I is automatically a type at every higher floor. But Rocq takes this route, so you can usually forget the level. Lean does not. Each type sits at exactly one floor, and the next idea, universe polymorphism, is how Lean keeps the tower workable instead. Look back at the polymorphic identity. There's a hidden constraint hiding in that line. Alpha colon type actually means alpha colon type 0. So this it only works on ground floor types. But we'd also like to feed id a type itself, to apply it to type 0, which lives one floor up. The naive call doesn't type check. The fix is universe polymorphism. Declare a universe variable U, and the same id works at every floor at once. The kernel instantiates U afresh at each call site. Read it as for every universe level U, and every type alpha at level U, a function from alpha to alpha. One definition, every floor of the tower. Here's the question that decides the shape of the whole system. If you quantify over every type in some universe U, where does the result live? The cautious answer, and the one type universes use in Lean and Rocq, is predicative. If the body T of alpha lives in type J, the whole pi lands at the higher of J and I plus 1. At least one floor above type I and never below where the body already sits. That was just a specialization of the general dependent pi rule. The universe of a pi is the max of its domain's universe and its bodies. Plug in type I as the domain, which itself lives at type W plus 1, and the predicative formula falls out. The bold answer is impredicative. Even when you quantify over every element of U, the result still lives in U itself. That sounds dangerous. Girard's paradox lived in exactly this kind of self-reference. For type A universes, it really is dangerous. The standard fix is to keep every type level predicative and reserve impredicativity for one special universe. That special universe is prop, the universe of propositions. Lean and Rocq place prop at the bottom of the hierarchy. Its type is type 0. Inside prop, quantification stays inside prop. Quantify over every proposition and the result is still a proposition. Without impredicativity, these one-line definitions of true and false would not type check. They both quantify over all propositions, and the result has to itself be a proposition. Prop is the one floor in the tower where this is allowed. Everywhere else, the predicative rule applies. Step back for a second. We've said impredicativity is dangerous for type, but fine for prop. But what actually makes prop special? The answer lives in one design choice: how many inhabitants a type can have, and whether the system cares which one you hold. In type, terms of the same type can be wildly different. Nat has infinitely many inhabitants, and they're all distinct. Which nat you hold matters. In prop, the design goes the other way. Proofs are treated as computationally irrelevant. Lean makes same proposition proofs definitionally equal. Rocq keeps proof terms, but does not let ordinary programs inspect them as data. Which proof you hold is computationally irrelevant, and this is the design pressure that keeps impredicative prop from becoming a proof-relevant universe of data. Compare that with the type story. The Girard-Herkins collapse needed predicate spaces to stay in the same proof-relevant universe. Ordinary Lean and Rocq prop do not have that shape. That is the key difference. Even if you imagine proofs were relevant, a prop is a type of predicates, not itself a proposition. So for ordinary impredicative prop, the right high-level question is different. What forces proof irrelevance there? For ordinary impredicative prop, the more relevant result is Berardi's theorem. In impredicative CC, excluded middle together with propositional extensionality force proof irrelevance. You cannot keep proofs relevant if you also want classical reasoning over prop. The system erases that relevance for you. In Rocq, this is still not built into definitional equality. Without extra principles, proof irrelevance is not a theorem of the kernel. Lean makes the stronger choice. In Lean, proof irrelevance is definitional. The kernel itself treats two proofs of the same prop as the same term. No axiom needed. One concrete payoff. Code extraction can erase every prop-level term when it compiles your program. If which proof you held never mattered, the compiler can drop the proof entirely. Type theory carries two notions of equality. The first is definitional equality, written with 3 bars. The kernel decides it by reducing both sides. 2 plus 2 reducing to 4 is just a computation. No proof needed. The type checker sees it for itself. The second is propositional equality, written with 1 bar. The eq we built last episode. nd plus 0 equals n is not a computation but a statement about every n. It needs an actual proof, and typically by induction on n. One direction holds, the other doesn't. Anything the kernel sees as definitionally equal is provably propositionally equal. But propositional equality is more permissive. You can prove n plus 0 equals n without e plus 0 and n being the same closed term. UIP and axiom K are statements about the propositional one. The one with explicit proofs you can put side by side and compare. If prop is its own walled-off floor, here is a worry. A proof of a equals B lives in prop. But to use it, to rewrite a goal of type P of O into P of B, the proof has to influence something in type. Can a sealed-off prop reach into type at all? CIC opens a tightly controlled escape hatch. For certain small inductives in prop, those with at most one constructor carrying no real data, like ek, false, and aki, the recursor is allowed to eliminate into type. This is called large elimination or singleton elimination. That is exactly what makes subst work. The workhorse turning an equality proof into a coercion between types. Without large elimination, a proof in prop would have no way to act on a type-level goal, and equality in prop would be useless. The restriction to singletons is the price of safety. Eliminating a prop with multiple distinct constructors into type would let a type-level term observe which proof you held. And that breaks proof-irrelevance. Recall equality from the last episode. Defined inductively, one constructor refall. Now look at where the result type lives, in prop. That choice has a consequence. If equality lives in prop, and prop is proof irrelevant, then any two proofs of A equals B are themselves equal. This principle has a name: uniqueness of identity proofs, UIP. In Lean, with equality in prop and proof irrelevance built in, UIP is wired into the foundation. In Rocq, UIP is not part of the core theory. It is optional, added as needed. An equivalent way to state UIP is as a recursor. Axiom K says to prove anything about a proof that it equals itself, it suffices to prove it for refl. There is no other case. Compare with J, the recursor for equality we built last episode. J lets you eliminate any A equals B by reducing to the case where B is A. K goes one step further. When both sides are already you can reduce all the way down to refl. In plain MLTT, K is not derivable from J. It is a genuinely extra principle. Adding it is a real choice. Where does K actually show up? Dependent pattern matching. The tempting Ogda definition is one clause. Pattern match the proof Piessens as Raphael. But that case split silently says every self-equality proof is reflaw. That is exactly the extra deletion step named by K. This is exactly what Ogda's without code rejects. With K off, equality eliminations must be phrased through J, where the two endpoints are allowed to vary. You cannot collapse a loop proof at A cameras Yesiu just by matching it as reflaw. Lean puts equality in prop and bakes proof-irrelevance into the kernel. So UIP and K come along for free. Rocq has the same impredicative prop, but proof-irrelevance is not definitional. UIP follows automatically for types with decidable equality. For general types, you state it as an axiom. Ogda parts ways. Its standard equality lives in type, not prop, and axiom K is a compiler flag, with koan makai without ko-off. Turning K off opens the door to homotopy type theory, where A equals B can have many genuinely distinct inhabitants, paths between points in a space. 2 episodes, 2 sides of the same formula. The right side became constructors and eliminators. The left side became a universe hierarchy with one impredicative floor, prop. That turns out to be exactly where the 3 big proof assistants disagree. Same engine, 3 dialects. The choices each system makes about prop, proof-irrelevance, and K shape the mathematics you can write in it, and the libraries that grow on top. Thanks for watching.